Hi everybody, Augie Kennedy here again with super awesome calculus. So, we're still in chapter 4, which is entitled Everything is Derivative. Basically we're using all sorts of applications of differentiation. Last time I very poorly taught you about L'Hopital's rule, and I taught you so poorly that I not only spent 25 minutes teaching crap, but I also omitted two very important things to remember. The first thing, and I only have a moment to go over them, but the first thing to remember is that sometimes you might not want to use L'Hopital's rule. Always look at a limit first and see if you can just eyeball it. Some limits you'll be able to take L'Hopital's rule over and over and over and over and over again, and you won't get an answer, whereas if you could just look at the limit, you'd realize, oh, it's very simple. A second thing is that sometimes you might need to use L'Hopital's rule more than once. If you need to, you just differentiate the function the first time, as you normally would, and then you go ahead and you differentiate it the second time. So for instance, if you have to differentiate, if the top is x squared over 2, if you have to differentiate this numerator, you get 1 plus 2x over 2, which is 1 plus x, and over e to the x. This isn't indeterminate, but go ahead. F over g prime, you'd get 1 plus 2x over 2 over e to the x, which the idea here is that that turns into 1 plus x over e to the x, and you can just use L'Hopital's rule again and get 1 over e to the x. Alright, so that's an idea of how you could use L'Hopital's rule multiple times. Now, finally, we have, we have the big problem from last time. The big problem wasn't really that hard. I asked you to check to evaluate this limit and use L'Hopital's rule if you can. And that was the limit as x approaches infinity of the quantity x minus the natural log of x. Now, we can just eyeball this and realize that as x approaches infinity, using direct substitution, we have infinity minus the natural log of infinity, which is infinity. Indeterminate difference, which we've already gone over, and as I mentioned when we did that trigonometric one, the idea here with the difference is to find a common denominator or to somehow separate this so that it's not a difference of indeterminate forms. And the key here is to divide everything by x. Divide that quantity by x. That gives us the limit as x approaches infinity. Factor out an x times 1 minus ln x over x. X times x minus ln x over x is the same thing as x minus ln x. That's an algebraic trick that if you got it, you probably got this right. We're not done yet, but you probably got it right if you got that trick. That's the key observation to make, that this is the exact same as this. If you don't believe me, go ahead and multiply by x and you'll get this. So what does this say? Well, let's go ahead and let's write this form again. We now have limit as x approaches infinity of x times 1 minus ln x over x. Using direct substitution, it really doesn't help us because we know that we have infinity times 1 minus 0 over 0. But remembering your limit laws, we can compute the limit as x approaches infinity of ln x over x. This is 0 over 0, which is an indeterminate form, or it's infinity over infinity rather, which is an indeterminate form. So we can use L'Hopital's rule. Differentiating both the top, we get 1 over x, and the bottom, we get 1. We realize that this limit is the limit as x approaches infinity of 1 over x, which is 0. If the denominator gets huge, that becomes very close to 0. So, let's go ahead and see what we've got now. Limit as x approaches infinity of x times 1 minus 0. Well, that's very simple, because if x is infinity, we then have infinity times 1, which is just infinity. So sure enough, the limit to the original question, x minus ln x, is infinity. At infinity. So there you go. That is the answer to the big problem. Now today, we're going to really apply a lot of these things into a very big lecture on graphing. By the end of this lecture, you should be able to graph just about any function by analyzing several components. And let's look at what some of those components are. The first, whenever we need to graph a function, we need to ask ourselves these questions. What is the domain of the function? In other words, where is the function defined? Where is it not defined? Second thing we need to ask, what are the intercepts? We know how to find y and x. We know how to find the y-intercept. That's what f of 0. And we know the x-intercept is where f of x equals 0. If you can find, you should be able to find the y-intercept. If you can't find the x-intercept, don't worry about it. C, symmetry. Is it symmetric? If it's an even function or an odd function. If it's one of those two, it's going to be very easy. You only need to graph half the function, and then you can realize, hey, wait a second, the other half of the function is just a mirror image. Symmetry makes it easy if you can figure that out. Remember, even function is f of negative x equals f of x, that's even. And negative f of x equals f of x is odd. I'm pretty sure that's right. D, asymptotes. 3 types of asymptotes. There's the vertical asymptote. We know that one. There's that's where you'll have something over 0 usually, an undefined part of the domain. You have horizontal, which is the limit at infinity. We learned how to test that before in chapter 2. And finally, we have something called slant asymptotes, which I'll talk about at the end of this. I won't try to give you too much with slant asymptotes, but some teachers might. Then we have increase or decrease. We know that's when f prime x is greater than 0, it's increasing. If it's less than 0, it's decreasing. We want to find those intervals. We want to find min and max. We can do this using the first or second derivative test. We want to find concave up or down and inflection points. And we know how we can test that using the second derivative of the function. And then finally, we'll go ahead and we'll sketch the curve. So, domain, intercept, symmetry, asymptotes, increasing, decreasing, minimum, maximum, concave, up, down, and inflection, and then go ahead and draw it. Sounds easy, right? Well, all right, here's what we're going to do. We're going to do an example. And you can use this example on just about any function. The key, one of the keys to any good example or any good graphing is if you have some idea of what the original function looks like. For instance, if you've got like e to the sine x, well, you know what sine x looks like, and you know what e to the x looks like. And while the combination might not be correct, you would have a pretty good idea that because e to the x is never going to have a negative output, that it's going to be above the x-axis at all times. So it just helps to have an idea. But for this one, we're going to do f of x equals 2x squared over x squared minus 1. Pretty easy, but we're going to use this. I don't think you can read that. It's going to be hard to fit everything on this tiny little board. F of x equals 2x squared over x squared minus 1. Okay? First thing, we want to know the domain. Where is it defined? Where is it not defined? Well, we know the domain. And I'm going to erase the domain in a moment because we've got a lot of operations to do here. The domain is going to be defined wherever the denominator isn't 0. And the denominator is going to be 0 at 1 and -1. So we say the domain is from -infinity to -1, and then not -1 itself, between -1 and 1, not including 1 itself, and from 1 to infinity, using that little u to connect them. All right? That's the domain of this function. So we already have a pretty good idea that we're going to have asymptotes because we have 2 points, -1 and 1, where the denominator is 0. 1 minus 1 is 0. -1 squared is 1 minus 1 is 0. Now, intercepts. What is f of 0? Well, let's find out. f of 0 equals 0 over -1, which is 0. So the y-intercept is going to be 0. If we were to solve this function, 2x squared over x squared minus 1 equals 0, you'd find that in fact the x-intercept is also 0. So whatever this is, there's going to be an intercept right at the origin. All right. Now, is this function symmetric or is it not? Well, let's check it out. Let's check for even first. 2 f of times -x squared over -x squared minus 1. What is that? -x squared times -x squared minus 1. Let's figure it out. 2 times -x squared is x squared over -x squared is x squared minus 1. We realize that this function, f of -x, is the same as this function, f of x. Therefore, 2x squared over x squared minus 1 is even. So that helps us a lot. We're just going to graph the right side, the positive side, and then flip it around the y-axis, and we'll have the graph. So we have an even function with x and y intercepts at 0, and a domain that's not defined at 0 and -1. And if you check the limit, you'll realize that, in fact, for asymptotes, we're going to have a vertical asymptote at -1 and 1. Now we need to check the horizontal asymptote. I'll tell you right now, there's no slant asymptote here, so don't worry. Horizontal asymptote, we check the limit as x approaches infinity at 2x squared over x squared minus 1. And, you know what? We can totally do this. How can we do this? Well, by dividing by x squared. Let's go ahead and divide. We've got x squared on top, x squared on the bottom. And let's write it -1 plus x squared, just to make this a little bit easier. We've got, we've got 2 over 1 minus 1 over x squared. All right? And that limit at infinity is just 2 over 1, which is 2. So we have a horizontal asymptote at x equals 2, y equals 1, -1. We have vertical asymptotes. Now, moving right along. That takes care, we've defined domain, intercept, symmetry, and asymptotes. Now we need increase intervals, decrease, and all of that derivative stuff. So instead of really, what we're going to want to do now is, now that we have the function, we're going to need to find its derivative. So f prime x, you're going to want to use the quotient rule, f, g, and we're going to skip the computations on the quotient rule for time purposes. if you use the quotient rule here, you'll figure out that the derivative is negative 4x over g squared, which is x squared minus 1 squared. And what you can do there is you can realize that f prime x is greater than 0 when x is less than 0, and f prime x is greater than 0, or is less than 0 when x is greater than 0. So therefore, or as long as x, it can't equal 1, but that's just because it's an asymptote. Yeah? Yes. So we know that it's going to basically be, alright, fine, x can't equal 1, x can't equal 1, or negative 1. So what that means is that f of x is increasing on the left side and decreasing on the right side, which gives us an idea, because we remember it's symmetrical, that there may be a parabola type thing going on here. If it's increasing on one side, decreasing on the other, and it's symmetrical, makes us think. So it's increasing at low numbers, decreasing at high numbers. Okay? Now, taking that derivative, we can find the second derivative. And the second derivative, once again, using the quotient rule that for time we're going to skip, is 12x squared plus 4 over x squared minus 1 cubed. Okay? Now, we need to find where we're going to have inflection points. Well, we know that f prime of x is going to be positive. It's going to be concave up, a positive number, wherever this x squared minus 1 is not negative. And it's going to be not negative, x squared minus 1 is not negative, it's positive, wherever x is between negative 1 or 1, it's going to be negative, so it's going to be positive at the absolute value of x. So it's going to be concave down between 1 and negative 1. Everywhere else, concave up. Going to sneeze. Alright, so we've got the derivative. We know where it's increasing. Left side increasing, left side increasing, right side decreasing. We know it's concave up on the left side, concave up on the right, concave down in between 1 and negative 1. We know almost everything about this curve. Let's go ahead and sketch it. Alright, so here's the curve. What do we know? We know it's not defined at negative 1 and 1. We know there's a vertical asymptote there. We know that at x equals 2, there's a horizontal asymptote. Okay? What else do we know? We know that it's symmetrical. It's even, so we're going to copy what's ever on this side. We know that it is increasing, or that there's an intercept right here at 0, 0. We know that it's decreasing until 1, or on this side it's decreasing. So it's going to be decreasing, concave down, approaching that asymptote. Decreasing, concave down, approaching that asymptote. And on this side, we know that it's concave up, so it can't be starting here, because that would be concave down. It's going to be concave up and decreasing. So it should look like that. Concave up and decreasing. Great. And we know that it's even, so it's just going to be a mirror image along the axis. And there's your function. So we used all of our different techniques to learn how to graph that, and that is in fact basically how that function looks, except it's drawn much better. My drawing sucks. Finally, the concept of the slant asymptote. I'm going to mention this so that you can know about it. If it shows up, great. If it doesn't, that's great too. If you have a function like this one, f of x equals x cubed over x squared plus 1, you might have a slant, or you will have a slant asymptote. Remember we talked about polynomial degrees? If the degree of the numerator and the degree of the denominator, if the degree of the numerator is the degree of the denominator plus 1, you'll have a slant asymptote. 3 equals 2 plus 1, slant asymptote. What that means is that if you remember from your algebra class, we can do polynomial long division. We get x squared plus 1 over x cubed. We can divide those like a polynomial, and we realize that this is the same as x minus x over x squared plus 1. That's what the numerator really is. So f of x equals that. It's basically an improper fraction that hasn't been factored well. So, I mean, that's basically it. You're going to have a line. The way we can, yeah. Basically, you find this remainder, you simplify, it's going to be your asymptote. You'll find that this is going to turn out to be y equals x if you go through the process. That means, it means that if you have a function like that with a slant asymptote, the remainder of the long division, that means that the function is going to be approaching that line. That's a slant asymptote. You might see them, you might not, but you're only going to see them under those circumstances. Degree is denominator plus 1. All right. Okay. So I feel like you have some tools now. So go ahead and graph. I've got a big problem for you. Go ahead and give it a shot. I want you to sketch the following curve as best you can. The curve is the square, y equals the square root of the quantity 1 minus x squared over x. All right. Go for it.